Hi everyone. Today we're going to be discussing inquiry and science as a practice. In this lecture, I'm going to introduce you to the four strands of science and where they fit into the 6E model. Then we're going to take a closer look at the scientific skills you will have your students practice in your own lesson plans. Many of you, when you picked your Louisiana State Standard that you were going to tackle in your lesson plan, had mentioned that you're going to have your students do one of the following: observe, classify, measure, communicate, infer, predict, experiment, hypothesize. And so today we're going to dive a little bit deeper into what that means and how you can incorporate that into the 6E model. And then finally, we're going to wrap up with scientific attitudes, because I think it's really important that no matter what we do in science, we keep it positive and we make science fun. So the four strands of science, what are they? These are interwoven in such a way they are inseparable from each other. I like to think about it as each strand as a color on an artist's palette, which work together to make a scientific masterpiece. So you know how every color works together for that picture. So what exactly are the four strands? Strand one is know, use, and interpret scientific explanation of the natural world. Strand two is generate and evaluate scientific evidence and explanation. Strand three is understand the nature and development of scientific knowledge. And strand four is to participate productively in scientific practices and discourse. Well, that's nice, Hollander, but what does that all mean? So let's dive into each strand. Strand 1, understanding scientific explanations. In science, your students are going to be learning the facts, theories, laws, and other scientific concepts. Understanding means knowledge can be applied in a new way, like creating a model or generating a scientific argument. In terms of the 6E model, we would engage the class and explore a topic. So you want to make sure you take ample time for students to explain and make connections while you guide them as needed. And you would need to assess how the knowledge is applied in new ways, or basically, you need to assess do your students understand these concepts. Strand 2 is generating scientific evidence. We need to be able to design and analyze an investigation. Not only should students collect data, but they should also be able to analyze it. So in your lesson plans, please make sure that if you are having students collect data, that they are also taking a minute to look at it. Data should be used to create an argument as to why our initial understanding was incorrect, or maybe it's used to defend that our understanding if the data upholds it. Also, you need to know when our data collection is too limited to draw a meaningful scientific conclusion. So, for example, if you're doing an experiment and it involves bugs, and the students only run the experiment once, and with a limited number of bugs, can we really make that statement that all bugs react to a particular stimulus in the same way? So how does this get incorporated into the 6E model? Well, you want your students to engage in data collection and then use that data to support their explanation. Engagement and elaborations allow students to design their own investigation and collect data based on their own questions. Strand 3 is reflecting on scientific knowledge. Science has its own vocabulary, history, and ways of producing knowledge. So how do you incorporate Strand 3 into the 6E lesson plan? Well, first, you need to give students ample time to explain in your lessons. Students could be doing different experiments but getting the same results, or maybe they're doing the same experiment but getting different results. How can that be? So really having your students take a minute to explain what they're observing, why they think they're observing, comparing their data sets to their peers, and thinking about what might be going on will be very helpful in your scientists reflecting on their knowledge. And then elaboration allows students to generate new ideas and questions based on their explanations. I apologize for the typos in this lecture. I will make sure they get fixed up before the next one. Strand 4 is participating productively in science. How do you get all your students on board to think like scientists? And I think this is really important. Before you even bring out whatever they're going to be observing, whatever experiment they're going to be doing, You need them to get all on board to think like a scientist. So I would have my students know that I expect them to be able to construct and present their scientific arguments to others. If we're going to do this experiment today, I expect you to tell me what you think is happening and why. You need them to understand that you expect them to be willing to ask and answer questions because that's what scientists do. And you need your to expect your students to be skeptical but still willing to change their viewpoint. So explain to them it's okay if your data doesn't uphold your original prediction or hypothesis, but you need to be able to understand why and be able to change it then. And where does this go into the 6E model? It goes everywhere. So, scientific skills in support of science practice. Scientific investigation involves asking and answering a question and comparing that answer with what scientists already know about the world. If you decide to become a scientist after all of this, that's what we do. We ask questions, we look at what other scientists have figured out, we then test our hypothesis of what we think is going on, and then we compare it to what other scientists have done to see, does other scientific data support this idea or negate it? Scientists use different types of investigations based on the question being asked. For example, it could be describing objects, events, organisms, classifying them, or actually doing an experiment. Your scientific skills might also use various instrumentation like beakers, magnifying glasses, or even just your students' five senses. And scientists make their results public or communicate them. That's why we need to expect our students to be able to communicate their science as well. And scientists review and ask questions about the results of their practice and other scientists' practices. You'll notice this picture of this small child and this woman out on a nature walk. And you're probably wondering, well, why did you put that out there? Well, I think sometimes when we think about science, we always think they have to be these formal experiments that involves lab coats and beakers and solutions, and that's not the case. Some of the standards that you guys have chosen discuss purely just observation, particularly those younger grades, those the K through 2 grades. And here we see this child out on a nature walk. Imagine all the different skills that you can apply on your nature walk. That student can observe things. You could ask them to make a prediction before you do an experiment, like dropping a rock from somewhere. Like there's all sorts of things that you could do just in your own backyard or on a nature hike. So the first skill we're going to discuss is observation. We need to teach students to use all five senses when they observe similarities, differences, and change in objects or events. Some of you chose learning standards that involve properties. Properties, that's you describing an object, but how the object looks, how it feels, how does it smell, how much does it weigh. There's a lot of different physical properties that your students can identify without any instrumentation other than what they were born with. So using all five senses reminds students that each sense can help them with understanding the properties of a particular object. Your book discusses the owl pellet investigation. If you're not familiar with owl pellets, barn owls eat small rodents and whatever they cannot digest, so fur and bones and certain vegetation, they end up regurgitating into these little pellets. And you can have your students investigate these pellets. So here's an example of an owl pellet investigation. You could pass around the pellet and allow students to touch it and ask, what do you think is in there? You can have students make predictions based on knowledge from teacher lecture and children's lit. So you could read stories about owls and then discuss where they live and then think back like, well, based on where they live, what do you think they're eating? What do you think is in this thing? And then you need to allow your students to explore the pellet and allow students to elaborate what they observe, like what type of bones are in the pellet, compare those bones to the charts of rodent bones you have, and also compare what their pellet contains compared to their peers. You can then have your students explain How many animal remains did they find? How did the bones you found compare to those in the guide? What do you think the owl ate? And where do you think the owl lives? So this is one way that students can use the power of observation through a scientific inquiry lesson. You can also use owl pellets for classification. Classifying is grouping objects by common properties such as color, shape, and size. Dichotomous classification is grouping events or objects into two groups. And I'm going to tell you this right now. I would think that you could easily do multiple classifications with students that are in the fourth grade or above. So in the 6C model and owl pellets, during the exploration part, you could have students think of one property and sort all the materials in the pellet based on that property. Maybe that property is hard, and then they take all the hard stuff and they put it in one pile. And then your explanation could be, what properties can you use to sort the objects? Like, why did you pick that one? What other properties could you pick? And then sort that pellet using those properties. And then you could have your students classify into more than one category, like bones, fur, and vegetation. In addition to that, you could also present your students with different species of owls and their pellets, and they could compare what their barn owl pellet looked like compared to a tawny owl, a kestrel, a little owl, or a jackdaw. And then they could describe, where do these owls live? What do they normally eat? And why do you think their pellets look so different? So there's a lot of different ways that you can do classification with your students. Other things you need to think about with your students is measuring. Most young children find it challenging to work with standard units of measurement until they're about 7. So if you're planning on teaching kindergarten or first grade, you may not want to be busting out those rulers and those weights just yet. However, when you do start measuring in your classroom, you will be using the metric system. Why does science use the metric system? Well, the metric system is defined in multiples of 10, and all scientific investigations should be done with the metric system, since all of science is done in the metric system. And the most common measurements are meters for length, liters for liquid, and grams for weight, and Celsius for temperature. So how do you do measurement inquiry? And I love measurement because you can incorporate it into social studies plans and math lesson plans. So in the engagement of your lesson plan, you could give your students a scenario or a children's lit that involves a journey. And then you could have them try to measure that journey. Or you could do something even more simple and you could give your students some matchbox cars and go out on the blacktop of your playground. Then the students are going to predict during their exploration a specific distance, and then they will measure it. During the explanation, your discussion can focus on the measurement unit of length and the appropriateness of that unit used. So for example, you probably are not going to be using centimeters if you are rolling a matchbox across a flat blacktop. You might be using meters instead, and you can discuss when you use certain amounts of measurements. And then elaboration could be looking at other units of measurement, like the weight of the matchbox cars or the temperature outside when rolling the cars. So that could be a way to elaborate. We also want our students to be able to communicate science. Converting the information or data obtained from your observations into some form another person can understand. So communication does not mean that you have your students write a lab report. Communication can be your students drawing pictures of their observations, accurate pictures, drawing diagrams, filling out data charts and graphing that data, or even creating some sort of model. So those are alternative ways you can have your students communicate their science. Another thing that your students are going to be learning how to do is infer. Inferring means to interpret or explain what we observe using the available information. So what exactly is inference? It's a conclusion you reach by applying logic to the evidence you're given, an explanation or interpretation based off of one or more observations. So if you do a demonstration with your students, you can then ask them to make an inference. Remember, an inference is not a guess because guesses are often based on little or no evidence. And making inferences will give meaning to what you are observing. Inferences people make may differ depending on what each person's past experiences and observations. So, for example, some students might think that hoverboards are a lot of fun because of their past experiences, and they think that everyone should have one. But then other students, they may have broken their elbows on that same hoverboard, and they might not like those toys at all. Before you begin your thinking process, think about these questions. What do I observe? What do I already know? How can I explain what I observed, and what does this mean? So those would be the types of questions you would pose to your students after they watch a demonstration or do a particular experiment. Here's an example that include an observation that is followed by an inference. So, for example, if you're opening up a book and the page in this book is yellow, you could infer that either the book is really old or that the book's paper was dyed yellow to make it look old. Many of you are going to have your students make predictions. A prediction is a forecast of future observations based on inferences from available data. And so your book goes into this example, which I actually like a lot. It has students record and graph the time it takes a candle to go out under glass jars 5 times. So you would have your students light a candle and then put a 200 ml glass jar over it 5 times, and then do the same experiment with a 300 milliliter jar, and then ask, how long do you think the candle will burn in a 250 milliliter jar? And you'd have your students make that prediction and explain how they came up with that prediction, and then allow them to do their experiment to see if their prediction is correct or not. And if it is correct, then you can have them elaborate on how they got to the correct prediction. And if it's not correct, then they can continue to explore. Something that's really important, in a lot of the standards you chose, the students need to develop an experiment. And an experiment is only going to be as successful as your students' ability to come up with a hypothesis. So how do you get your students to form ideas they want to test before they manipulate an object? Basically, they need to learn how to write a hypothesis. A hypothesis is an if-then statement. An if is almost always going to be the variable. So if I put my plant in a dark room, then it will not bloom. And this is due to, and your rationale is going to be using your prior knowledge or knowledge obtained through the teacher's lecture. When you have your students designing the scientific process, remember that they need to understand their independent and dependent variables and their controls. So here in this experiment, we're feeding plants soda, juice, or water. So the one thing that you change and limit to only one in experiment is going to be your independent variable. So in this case, your independent variable is what you're feeding the plants. Is it going to be soda, water, or juice? The dependent variable is the change that happens because of the independent variable. So in this case, it'd be the height of the plant. How much did your plant grow? And your control is going to be what you're going to compare everything to. So in this case, your control would be the type of plant used, the pot size, the amount of liquid that you apply to the plant, soil, the number of hours it's in sunlight. Those would all be the different controls to your experiment. This is a very difficult concept for young learners, and I highly recommend that you start drilling it into their brains early and have them practice identifying these different variables within the scientific process. And finally, scientific attitudes. I think what kills me the most as a science instructor is when I get you all into my classroom and you tell me how much you don't like science because you had such crummy science teachers. And it breaks my heart because science is so much fun. And in elementary school, you have these kids who are naturally curious. So play it up. Use their curiosity to your advantage. Don't squish it. Don't be like, nope, that's not going to work. No, just let them explore. You also have students that are very inventive. Allow your students to solve problems in creative and novel ways. I know a lot of elementary schools that you'll be going to are going to supply you with kits for you to do science experiments with, Those kits are great sometimes, but what they do is they take the inventiveness out of it because you're not allowing your students to explore every single avenue to solving a problem. Scientific attitudes. You also need to consider how you are going to help your students critically think and how you're going to harness their ability to critically think. So you need to ask questions like, does this data uphold your original prediction? How can you explain this phenomenon based on your observations? What can you predict if we do this next time? So I think like really getting your students to critically think is important. And then finally, persistence, especially when activities take weeks. You need to get your students interested. And sometimes experiments don't always work, or students need to try things a couple ways and a couple different times. There's this attitude that we're getting right now with our students where they feel like they always have to be right, particularly our female students. And science, unfortunately, there's a lot of times when they may not be right, they may not know the right answer, or they may not get the right answer on the first try. And that makes students very uncomfortable. So please remain positive with your students when you're doing various experiments and teaching them various scientific concepts. Thank you guys so much and have a great day.